Sorry about that, which is a tree of projective lines that meet at nodes, and there are spokes of equal length that emanate from some central component. We have an order R automorphism that acts on this curve that basically sends one spoke to the next spoke. And then we have two distinct fixed points of this automorphism. And then there's n labeled light orbits of heavy points, marked points, and then there's an additional heavy orbit of marked points. And then these are two examples of what these curves might look like. Hopefully you can see this. These are both 2-2 curves. The top one is length 1, and the bottom one we would say is length 2. We can formulate this moduli space a little bit more combinatorially using Rn trees, which are just, I'm pretty sure, the dual graphs of our Rn curves. So we use nodes to represent each component, and then each marked point is a leaf that's going to be incident to the node that represents the component it's on the curve. I specifically was focusing on the dual boundary complex, which we call delta Rn. And we can think of this as a simplicial complex encoding of the combinatorics of our boundary divisors and how they intersect. With our dual graphs, we represent a dual graph with length k is represented with a k-1 simplex. And then very informally, connections between these simplices are determined by edge contractions. So this is an example of what that might look like. Here on the bottom, this is a length 2 graph. So it's represented by this one simplex. And then here you can see on the left, if we contract this like the inside edge on each spoke, we would get this one length 1 graph here. So that's represented by the 0 simplex. And on the other side, we do the same, but now with the outside components on each spoke. And if we continue doing this for all of our graphs, this results in an n-1 dimensional simplicial complex. These are a couple examples of just some like simple dual boundary complexes that I calculated for my thesis. On the left is delta 2,2, and on the right is delta 3,2. I started doing some like partial calculations with like n higher than 2, but it gets very, very hard, and the number of trees expands, it grows very quickly. So I didn't quite finish that, but the goal of my thesis was to use, leverage the combinatorics that are present in this moduli space to calculate topological and geometric properties of our dual boundary complex. The ones I focused on specifically were Euler characteristic and homotopy type. And the result I ended up getting was this right here was a hypothesis for what the Euler characteristic is that one of my advisors had coming in. And we wanted to prove this using combinatorics, and that's what we ended up doing. I don't quite have a result on homotopy type, but in my thesis, I did discuss a conjecture as well as two possible approaches that we might use to prove that conjecture. So with any remaining time, I'm just going to very briefly go over some of the methods we use to get the Euler characteristic. First, we started out with this recursive formula. It's recursive on n that counts the number of simplices of dimension k in our dual boundary complex, or equivalently, this is going to be the number of graphs of length k plus 1. And we basically got this formula by counting the number of ways that you can get a stable tree by adding another orbit of marked points. And then the main method we used was generating functions. So using this recursive formula, we get this exponential generating function right here, which, as you see, this is a first order differential equation. So solving this first order differential equation, we get this expression here. And then we basically took the alternating sum of this over k to get an exponential generating function for the Euler characteristic. You can simplify it here. We use the binomial theorem to simplify that pretty nicely. And then finally, we just compared this generating function to the exponential generating function from the hypothesis we had for the Euler characteristic. And we're able to show that these both simplified to the same expression, and thus our hypothesis must be true that the Euler characteristic of our dual boundary complex is equal to 1 minus 1 minus r to the n. The end.